Welcome to our next presentation on ICT Project Engineering. This presentation is on our preferred project model for the delivery of technology projects. The technology project could be either software, an air-to-air missile, telecommunication network, life safety radio communications. The list of technology projects goes on. The V model dates back about 40 years. Over the 40 years that this model has been in use, for every dollar spent in requirements and design, saves $10 during construction, which ends up saving $100 during system sustainment and obsolescence. In respect to this presentation, we would like to discuss technology project delivery in relation to smart buildings. Smart buildings are a new building technology that is an integrated, unified solution that encompasses networks, software, and hardware, with various subsystems that vary from inputs into tenant systems, building automation and optimization process, environmental control, security, life safety, and health monitoring and control systems. In this coming decade, smart buildings are intending to significantly alter the building technology landscape. In summary, the changes are expected to be 1. The technology will be fully IP, IoT network-centric, and completely unified. 2. Pick, plug and play utilizing IP over single-pair Ethernet. 3. Buildings will have operational technology, OT networks, which will need to be managed, with IT industry sustainment practices and obsolescent life cycles. 4. The software integration and management will be more important than the hardware. 5. Subsystem, system and network firmware and software patching will need transition planning and testing. 6. Cybersecurity. 7. Infrastructure engineering needs to be transition-proof. The IT components will need to be quickly installed, integrated, fully acceptance tested, ran in parallel with the existing, shadowing for at least 6 months. Then the existing, obsolescent equipment quickly removed. All this must happen without change or disruption to the building operations, or to the tenants. We may make a smart building infrastructure engineering presentation in the future. The V model provides fantastic guidance for the planning and realization of technology projects. The overarching goal of V model is to be able to put a smart building solution into service at day one, with a high degree of confidence that it will fully meet all its agreed requirements, which include strict safety and performance requirements. Honestly, the V model is simple and easy to understand and use. When we are engaged to do end-to-end projects, we like to use a modified V model, which is purposely structured for projects that we deliver. This model focuses on verification and validation activities early in the life cycle, thereby significantly enhancing the probability of 1. Building an error-free and quality solution. 2. Greatly improved cost optimization. 3. Significant reduction of variations and rework. And 4. Improve stakeholder and principal engagement to understand the user cases, cost benefits, risk, and sustainment. This sounds like an increase in specialist PM and engineering effort. Honestly, it is, when compared to current building services fees in this space. The cost increase is easily offset by the savings in risk removal, installation and integration rework, and variation costs. One last point that we would like to make: smart buildings are not quite here yet. Generally, most current smart buildings are automated buildings badging themselves as smart buildings. Smart buildings are slowly coming online. They will increase exponentially, become a core building solution and business influencer for developers. If we had to state a single reason on why the industry is bearing the expense of smart buildings, basically, it is to further optimize energy and resource utilization and improved operational management. Now that we have set this one use case for the V model, let's discuss the V model. Firstly, what is a V model? The V model is a graphical representation of a system's development lifecycle. Additionally, it is used to produce rigorous development lifecycle and project management plans. The left side, the verification side of the V, this represents the decomposition of requirements and the creation of system specifications. Additionally, the requirements need to be verified against the higher level requirements and the mandated needs. The right side, the validation side of the V, represents the integration of parts, subsystems, and systems, and their validation. Furthermore, this can partially be done on the left side also. To claim that validation only occurs at the right side is not quite correct. The easiest way is to say that verification is always against the business and engineering requirements. Validation is against the real-world construction or the application of user needs. To simplify this further, validation can be expressed with the query, "Are you building the right thing?" And verification can be expressed with the query, "Are you building it right?" We won't be discussing sustainment or obsolescence in this presentation. This may be a topic for a future presentation. Here are several verification phases within the V model. Each of these are explained in detail in the following few minutes. Business and operational requirement analysis is the first phase in the development cycle where the requirements are understood from the client and stakeholder perspective. This phase involves detailed communication with the client to understand their expectations and exact requirements. This is a crucial activity and needs to be managed well, as most of the clients are not sure about what exactly they need. Engineering requirement analysis is the second and third phase in the development cycle where the requirements are converted into engineering requirements, costed, tested, and fed back to the client and stakeholder. This phase may involve options being tested, recosted, and requirements adjusted to create a solution that can be built and meets all business requirements and project requirements and constraints. This phase involves detailed communication with the client to manage their expectations and alter requirements, if required. This is a crucial activity and needs to be managed well. Typically, Phase 1, Phase 2, and Phase 3 create an independent feedback loop. Usually more than one technical approach is proposed, and based on the technical and financial feasibility, the final decision is taken. Once the project has clear and feasible requirements, and these requirements captured and detailed, it is time to document the concept of operations, also known as use cases of the system. There may have several operational scenarios that the system must cater for and must deliver the correct system output. As an example, hospital operations will have different actions based on the situations and threats like security or an epidemic, which may be addressed differently at ward level, a building level, or campus level, and enacted at any given time, for any given duration. The user acceptance test plans, sometimes referred as scenario testing, are prepared at this stage. The high-level design is also referred to as the concept design or even as the schematic design. The system design is broken down further into modules taking up different functionality. The role of the design concept is a means to define the desired outcome of the systems. This can be prepared as part of 1. The design team's initial response to the concept of operations and the requirements, which forms the project brief. This allows the client's team to ensure that the design team understands all the requirements and expectations before commencing the detailed design or developed design phase. 2. The client's engineering team, developing the high-level design as part of a reference design, explaining the expected solution based on the concept of operations and the requirements. This will allow the design team to directly commence the detailed design or developed design phase. The high-level design will document the understanding and detailing of the complete network, hardware and software setup for the solution that is under development. The data transfer and communication between the internal modules and with the outside world and other systems is clearly understood and defined in this stage. With this information, integration acceptance tests can be designed and documented during this stage. Detailed design is also referred to as low-level design. It is important that the design is compatible with all the modules and systems in the smart building system architecture and the other external systems. In this phase, the detailed design includes the installation and integration specifications of all the system modules required. This documentation must include clear layout, mounting details, hardware and software schematics that can be built by the construction, installation, and integration team. All the test plans, including the factory acceptance test plan, must accompany the IFC design package. Construction phase is a separate phase outside the verification and validation phases. Construction is typically broken into 4 stages: initiation, planning and pre-construction, construction and installation, installation monitoring and control, which is performed concurrently within construction. It must be noted that factory acceptance testing, known as bench testing, needs to take place within the planning and pre-construction stage. Each of the different validation phases in the V model are explained in detail in the following few minutes. Site acceptance testing, also known as subsystem or unit testing, is an essential part of the testing process. It greatly assists to eliminate the maximum faults and errors at a very early stage. Each subsystem, i.e., security, CCTV, OT network, is tested as a standalone system, ensuring that each subsystem is installed and configured correctly. When that is completed, and all subsystems have been accepted, then subsystem integration testing commences. Integration acceptance testing is performed to test the entire system functionality, subsystem coexistence, communication modules, and the network. Integration tests uncovers the compatibility issues with the other subsystems within the total environment. It also discovers the non-functional issues such as load and performance defects. Furthermore, by way of an example, if a subsystem integrator updates the firmware within their module, integration testing must cease. The entire subsystem must go through site acceptance testing before integration tests must commence from the beginning again. User acceptance testing is sometimes referred to as scenario testing. This testing phase is used to ensure that the system operates as required for each of the business operational scenarios and that the system also meets all the documented requirements. As a final note, the V model does have advantages and disadvantages. The advantage of the V model method is that it is very easy to understand and apply. The simplicity of this model also makes it easier to manage. The disadvantage is that the model is not flexible to changes and just in case there is a requirement change, which is very common in today's dynamic world. Depending on the requirement, it can become time-consuming to make the change. In summary, the advantages of the V model method are as follows. 1. This is a highly disciplined model and phases are completed one at a time. 2. Works well for projects where requirements are very well understood. 3. Simple and easy to understand and use. 4. Each phase has specific deliverables and a review process. The disadvantages of the V model method are as follows. 1. Initially, it has risk and uncertainty. 2. Not a good model for projects that are too complex, several packages, and object-oriented. 3. Not suitable if the requirements are unknown and not verified prior to design. 4. Not suitable for the projects where requirements are at a moderate to high risk of changing significantly. 5. Not suitable if the requirements are unknown. 6. Once a system is in the testing stage, it is difficult to go back and change a functionality. This may require testing to commence again. In summary, the following objectives are intended to be achieved by a V model project execution. Minimization of project risks. The V model improves project transparency and project control by specifying standardized approaches and describing the corresponding results and responsible roles. It permits an early recognition of planning deviations and risks and improves process management, thus reducing the project risk. Improvement and guarantee of quality. As a standardized process model, the V model ensures that the results to be provided are complete and have the desired quality. Defined interim results can be checked at an early stage. Uniform product contents will improve readability, understandability, and verifiability. Reduction of total cost over the entire project and system life cycle. The effort for the development, production, operation, and maintenance of a system can be calculated, estimated, and controlled in a transparent manner by applying a standardized process model. The results obtained are uniform and easily retraced. Improvement of communication between all stakeholders. The standardized and uniform description of all relevant elements and terms is the basis for the mutual understanding between all stakeholders. To conclude, smart buildings are an IT technology solution, and consideration must be made to deliver this as an IT project. The design, documentation, installation, integration, testing, commissioning, and acceptance should be delivered within an IT project framework. Until our next presentation, take care.